reference point?
So the force on 3, when you plug into the equation, the force on 3 is going to be relative to the other charge.
Okay, so the
So I have
other,
the subscript 4 here, again, going with the notation that this is 4 and that's 3. This is establishing sort of my central.
'cause it's the force from 4.
Yes.
That's why it's R half 4.
Yes.
Okay, gotcha.
It's the force from 4.
Yep.
And so if it's going away from the center, it's positive, away from 4.
Correct.
Okay.
So we'll end up with a negative here, which means it's going towards 4,
Okay, okay.
because they're opposite charges.
There you go.
Wait, could you say that one more time?
If you break through this, you're going to get a negative number here because of that negative 4.
Yeah.
And so ultimately the direction will be negative R4 hat. So that means R hat is away, so negative would be towards. So the force is going to be toward, the force on 3 will be toward 4.
I got
Okay.
negative 0.432.
Negative 0.432.
At negative 43.2.
Alright, well, I'm not gonna go through it. I just put in what I just saw right there. That's it. It could be 43.
I got negative 43.2 as well.
We got 2 people on that.
Let's go with that.
Coulombs. Now, one thing I want to emphasize here is the fact that the question was, what is the force? If I had just written out what is the force on the first charge from the second charge, force is a vector. I am expecting a direction. I could have also expressed the exact same answer of, it's a one-dimensional problem. I could just say, well, let's say that way is positive, and so then my answer is 43.2 coulombs. Oh, sorry, that is wrong. Somebody should have called me on that. Newtons.
Oh, there.
I was gonna go on it.
Whoa.
It's a force,
Mhm.
Force.
and you've all just failed. The wolves did not teach you any better.
No,
No.
I was just testing you.
Oh. Glad I caught it. So if I define a direction, the positive direction in a one-dimensional problem, I get away with just expressing the answer as a positive number. All right, let's make it seem more difficult. Questions on this before I make it seem more difficult.
What is the E?
Oh,
It's for
It's like
exponent.
10
10 to
times.
the something.
9E9, this is in place of times 10 to the,
Okay, never mind.
Mhm.
Oh,
Yeah.
I see.
because calculators have the E or EE button that they use
Okay.
for that.
So if I put E, you get me.
No, all right, I will allow, if you want to, if the answer, if you want to write 4.32 times 10 to the first
Yeah.
newtons, I'm okay if you want to do 4.32 E1. I will accept that.
Okay. Good.
Well, for everyone else except you, Hector.
Except, I might have let.
Oh, what the heck, we'll throw you in there too. No, this is my concession. If you were writing a formal paper, don't do that.
Okay. Are we gonna do the formal paper this year?
No,
Oh, thank God.
unless you want.
No.
No, I like the formal.
We don't want to, but if you make us.
with the formal papers.
I will do this formal.
I don't like.
We'll do all the formal papers.
All right. Questions before I make it look more difficult?
Great.
All right, I got a 3 microcoulomb charge there. I've got a negative 4 microcoulomb charge there. 0.05 meters between them. And I got a negative 4 microcoulomb charge there. 0.05. We've already done the math. So I know that this force, ignoring direction, is 43.2. Yeah, 43.2 newtons. So this one is 43.2 newtons. So what's the total force acting on the 3 microcoulomb charge?
0.
Is 3 our center?
Yeah, 3 is halfway in between.
So,
0.
yeah, it would be. Wait.
0.
But you get two
If they're
negatives
going
on
to the
either
center,
side,
both
so
the
it'd
charges
just
are
be,
negative, so wouldn't they
be
negative?
double of that, so it'd be 86.4.
I'm saying it's negative 86.4.
I mean,
Alright, so we got basically 86, magnitude of 86.4 or magnitude of 0. It is one of those two.
Oh, the magnitude.
Well, and there's a video on this. You play strict adherence to the math or you think through it. A lot of times it's just a whole lot simpler just to think through it. What is the direction of, I have a negative charge there, a positive charge here, what's the direction of this force?
going to
acting
the
on-
right. If we, yeah,
And what's the direction of the force on this from this charge?
going to the left.
Oh, yeah.
They are in opposite directions. The total force is indeed 0.
Nice. I like that.
That does make
If
sense.
you, so this is, you think through the direction, you realize, oh, it's gonna be the same magnitude of force, opposite directions, so cancel out 0. Too many people will put down 86.4 newtons. Wow. Thanks for playing along.
Yeah, no problem. Just put me on it.
Now, let's play strict adherence to the math for the same thing. So I have 43, so the force on 3 from, we'll just call it A, we'll call this one A, this one B. So the force on 3 is the force on 3 from A plus the force on 3 from B.
Dr. Fox?
Yes.
Why does the 0 have a vector?
Because technically, if I have a vector on the left-hand side, the right-hand side has to be a vector.
Okay.
This is known as a 0 vector.
Okay.
The magnitude of 0 in what, I don't care what direction. Officially, there's a direction of, it doesn't matter.
Okay.
All right, so the force on 3 is the force on 3 from A plus the force on 3 from B. If we plug into the formal equation over there, this would be 43.2 newtons, negative R A hat, plus this would be negative 43.2 newtons R B hat. They do not have the same reference. So we need to somehow equate those. And I know at this point right here, our A hat goes that way and our B hat goes this way. They're opposite directions at this point. And so where this is, I know that our A hat is equal to negative our B hat. And now if you plug that in, you end up with 43.2 plus negative 43.2. Most of the time, though, think through it.
Wait, how did you assign the direction?
You got a negative in a negative direction, essentially. Just think about that.
R hat is always away from the reference. So R, since this is my A charge, our A hat goes away from it.
Oh, it's always away from whichever one's getting the force acted on.
Yes.
Can you say that one more time? R hat is always,
R hat is always away from whatever the reference is,
okay.
the source of the force. Questions here? Because now we'll make it look considerably harder.
No.
Considerably.
I guess I'll start here and work my way across and probably double back. All this is well and good, but I know what you're thinking. Where's the calculus?
Where is the
What's the calculus of those?
That
What's
was
the
on
calculus?
right here, man.
Right here. Right here.
Idle line of charge.
No.
For you purist, line segment of charge.
Directly below it.
0 to, we'll just say 5 meters. The total charge here is, Q1 is 3 coulombs. And then I've got a point charge over here. Q2 is, why not, 6 coulombs. I wanna know what is the force on 2 from 1.
And there's 5 meters. So,
Oh, I do need to tell you where Q2 is. Let's put this at, that's 0 there, let's make that 8 meters. You cannot legitimately just go, oh, let's pick the middle of the line to count as the charge. It does not work that way.
wait,
If I have spherically symmetric charge, I can do that, but I cannot do that here. I can't go, well, let's just assume the charge is in the middle. This is a calculus problem.
So the Q1 is that whole line segment?
Yep, I got this 3 coulombs spread out over 5 meters.
and then you got Q2 spread around 8 meters?
No, this 6 coulombs is just sitting right there. It's a point
Away
charge.
from the line of charge.
So does the 8 meters?
Yeah, 8 meters.
It's
8
the
meters
Q2
from
is
the
8
origin.
meters from the far end and therefore 3 meters from the close end.
Oh.
So basically, imagine I got a string that's completely charged, this is a 5 meter long string that's completely charged, and then I got another charge just kind of sitting right there, being affected by that string. Or line of charge, to use a fancy term. All right, we'll also make the claim that uniform charge distribution.
Uniform.
In other words, the charge density, the linear charge density is the same no matter where you are along the line. The symbol for linear charge density, which, same symbol that we use for linear density, or is that a mu? So linear charge density is basically charge divided by length. Regular density is mass divided by whatever dimension we're working in.
Oh.
Because it's uniform, dq
DT, right.
dx is the same, so
We get that, and then,
x.
okay. So then we put the limit,
We gotta do something before we get the limits, but yeah, we'll be doing limits. So when I say dq dx, that means anywhere along that 5 meters there, that no matter how big a segment I take, the ratio of charge to that length is the same. That's the meaning of uniform.
okay.
And the way you solve these problems is you first need to establish the charge, because our formula that was vaguely and poorly worded. Just look at magnitude for this second. K Q1 Q2 over R squared. The formula that we're given here is just basically 2 charges, but what am I using for a charge here? Because this is for 2 point charges, and I don't have a point charge, so I have to create one. I'm just gonna take a small little segment right here, which I'm gonna label DQ.
Oh.
It is an infinitesimally, but not 0, amount of charge.
Oh.
And so I'm gonna find the force, K dq Q2 over R squared. So step 1, define your infinitesimally small bit of charge.
Okay.
R is the distance from between the two charges. So R is this distance right here.
Oh, what do we call that? What do we call it? DQ to A.
What is the relationship between R and X?
What?
The relationship between R and X. This is where X is equal to 0, this is X equals 5. That's X equals 8.
Oh, 8 equals X plus R?
Or is it because it's
Yeah,
a variable?
yeah.
Whatever.
X, so DQ is at some position X. So X plus R is indeed 8. And so R is 8 times X.
Oh.
So I've got K, Q2, 8 minus X squared. And then I've got this DQ. I need to somehow get DQ in term, and that X in the same terms of the same variable. I have two variables here. I've got Q and I have X, but I really only want one. But I just happen to have a relationship over here between Q and X. I know that DQ is equal to my linear charge density times dx. So I can make that substitution, the lambda dx.
So do we know what the linear charge density is?
Oh, we can calculate it. I mean, it's gonna
So,
be,
so it'd be like a given or something?
yeah, I told you the charge and the length. So you can find it. Technically, again, for the purists, this would be df. Yeah.
Well. Too cool.
So to find the force, the magnitude of the force, well, I'll pull my constants out, k q2 lambda, and then integrate dx over 8 minus x squared. I now have a single variable. We now do limits of integration. What is the smallest value of x?
0.
It's not.
This x, this is the distance between.
Oh, 5?
Oh, wait, sorry, did this a little bit differently than I usually do. Yeah, 0 to,
To 5.
Five.
Yeah.
okay. We can do that.
Right.
We might end up with a negative here that I don't want, but, well, we'll worry about that. How do you solve it?
When you integrate, is this when you do the LN? Because it's in the, does
Oh,
this integrate LN?
If this were not squared, then natural log would be popping into it, but it's squared, so,
Okay.
Is U substitution?
yeah. U is equal to 8 minus x. Du would be equal to negative dx. So we end up with negative k q2 lambda
It's like brackets.
du over u squared. And my limits of integration can now change. So we stick in 0, we get 8. And we stick in 5, we get 3.
Okay. Now we got U squared at the bottom.
So this, looking at just the integral piece of it, integral from 8 to 3 of u to the negative 2 du.
That's an X, right, for the U equals 8 minus,
That's an x there. Yeah, that's an x.
okay.
Do you wanna do that? With the limit upside down like that?
Sure.
Okay.
So what is this
So like
integral?
this one.
U to the negative one over negative one?
Add one to the exponent, then divide by that, so I got negative u to the negative one, from 8 to 3. And so this piece becomes negative 1/3 minus 1/8.
Okay.
Whatever that is. All right, so the force is equal to K, 9 times 10 to the 9th, times Q2, which is 6, times lambda, which is just Q over L, that is 3 divided by 5, times this integral right here, but there is a minus sign there,
I
and
think
a
it's
minus sign there.
5/4.
That's 23 over 8. 23 over 8.
43 over 8.
Huh?
That's, no, can't be 43 over 8.
You're talking about, that, I'm pretty sure that's
Or is that the final
5
answer?
20, that one? I'm pretty sure it's 5/24.
5/24?
Yeah, cause it turns into 8 over 24 minus 3 over 24? 10.
My negatives cancel out. Not that that really matters a whole lot, because the way we're doing this. And then we get some just absolutely spectacular number. Let's see, the 5 cancel out, 3 cancels out, leaving me an 8. So I got 3/4 of 9.
3/4 of 9?
Yep. 0.75.
Something like that, okay.
So I got, let's just say 7.2 times 10 to the 9th.
It'd be 27 over 4, that way,
Pardon?
whatever that is.
Yeah, that, this isn't right. This is,
I got 1.62 times 10 to the 11th.
Well,
that does not feel right.
But,
See if I can write this more neatly. That's a questionable thing. So I have 9 times 10 to the 9th, times 6, times 3/5, times 5/24.